Night has folded itself over the roof, and the world outside has gone hushed. A thin line of starlight rests on the window frame, and somewhere far above, the Milky Way drifts like pale smoke. In this quiet, we can take a slow look at our nearest star. The sun feels homely morning on a kitchen table, warmth on winter walks, but it is also a restless engine. Tonight we'll wander, unhurried, through the parts that surprise us. Tangled magnetic fields that braid and snap, quick flares that paint space with radiation, and great billows of charged particles that can startle radios, satellites, and power lines here on Earth. We'll keep the pace gentle, the images soft, and the science clear, because knowing is a kind of shelter, and understanding turns worry into wisdom. If these calm night journeys suit you, a light tap on like and subscribe keeps this small porch light easy to find and helps another traveler reach it, too. Now the room is steady and the sky is wide. We'll begin the sun's story in a low voice and let the night carry the rest. Night gathers on a quiet hill, and the sky begins to bloom, orange, red, and pink unfurling as the sun lifts a bright edge over the horizon. That gentleness is the last step in a long voyage. Follow the light backward from the soft landing place at the back of the eye, through the thin blue film of air that bends and scatters it, across the 150 million kilometers of hush between worlds, and deeper still through the sun's layered body to the furnace at its heart. For 4.5 billion years, that heart has pressed nuclei together, turning a little mass into light and warmth. The star that gilds a kitchen table and warms winter shoulders was born in a stellar nursery from the enriched ashes of older suns, a glowing sphere of plasma matter so hot that atoms are stripped into ions and electrons held close by gravity and braided by magnetism, familiar as morning, and yet full of questions that invite us to look again. Begin softly at the outskirts, where the sun wears a pale crown. The corona, its outer atmosphere, stretches like a luminous veil many solar diameters into space. A patient watcher, the Solar Dynamics Observatory, a NASA spacecraft launched in February 2010 to understand how solar changes ripple through Earth's life and technology studies that veil in many colors of light, including colors our eyes cannot see. In extreme ultraviolet light, around 19.3 nanometers, the corona glows at about 1,000,000 Kelvin, and delicate arches, plumes, and streamers step forward from the glare. During a total solar eclipse, when the moon hides the blinding photosphere, the bright disk we usually see, the unaided eye can glimpse this halo for a few breath-held minutes. Instruments, steady and tireless, reveal threads, knots, and loops that daylight conceals. The landscape beneath that veil is full of weather. Bright knots that flare in ultraviolet images mark places where temperatures surge to many millions of degrees. These are solar flares, brief, intense bursts of electromagnetic radiation, released when magnetic field lines cross, twist, and snap into new patterns. The sun's turbulent plasma builds these fields, braids them tighter, and sets the stage for sudden release. Sometimes, that stored tension throws mass as well as light, a coronal mass ejection, when billions of tons of charged particles are hurled into space at hundreds to thousands of kilometers per second, hundreds of thousands to millions of miles per hour. In a blink, the energy in such events rivals the output of millions of nuclear weapons. There are weeks when the sun is especially lively. One such stretch in August of 2022 offered a steady parade of flares, each a reminder that the calm of noon is balanced by a restless engine behind it. Energy also escapes in quieter ways. Coronal holes, darker, cooler regions where the sun's magnetic field opens outward rather than bending back, act like open doors for the solar wind. Particles stream more freely through those openings, carrying the sun's magnetic signature out into the solar system. When those gusts brush Earth's magnetic shield, polar skies bloom with auroras, slow, rippling curtains of green, red, and sometimes purple, bright enough to paint snow, silent as frost. Ultraviolet light is a kind listener to the sun's outer layers, bringing forward features that visible light leaves muted. Filaments, also called prominences, rise as great arcs of plasma that follow magnetic rails. Some can appear within a day and hold their shape for months, stretching hundreds of thousands of kilometers into space, large enough to shrink Earth to a dot in comparison. Time-lapse films show their dance sped up so minutes look like seconds, yet even there the speed of their guided motion is striking, a sign of magnetic hands lifting and shaping glowing material. Not all of that material gets away. Some plasma is trapped, cools, and falls back as coronal rain, threads of light streaming downward, beautiful at a distance, still unforgivingly hot by earthly measures. At other times, tension builds until a structure unhooks and unfurls. A mass ejection blossoms and drifts outward like a bright seed. A strong one aimed our way can jostle satellites, disturb radio communications, and stress power grids. Many of these scenes shine clearest near 30 nanometers in extreme ultraviolet. Their frequency ebbs and flows with the sun's roughly 11-year cycle of activity, a rhythm that swells to a busy maximum and then quiets again. Looking with two ultraviolet colors changes the portrait yet again, as if switching lenses on the same landscape. At a color temperature near 600,000 Kelvin, one view traces quiet coronal loops arching from foot point to foot point. At about 2 million Kelvin, another view lights up hotter, knotted, active regions where energy is stored. Side by side, they show how a seemingly simple glow is layered. One event may be many processes braided together, each strand bright in a different part of the spectrum. The path inward crosses a very thin step called the transition region, perched between the chromosphere below and the corona above. It is only about 100 kilometers, 60 miles thick. Yet across that short distance, the temperature leaps from around 8,000 Kelvin to roughly 500,000 Kelvin, turning a slope into a cliff. For bearings from home, consider Hawaiian lava near 1,170 degrees Celsius, about 1,443 Kelvin, already beyond any kitchen fire. Even the cooler edge of the transition region leaves such lava far behind. In images taken near 160 nanometers, the region's fine structure peeks through bright grains and narrow lanes where heat and magnetism trade places with dizzying quickness. Set just below is the chromosphere, the last veil before the sun's visible surface. About 1,700 kilometers, a little over 1,000 miles thick. It shows a restless texture under ultraviolet light near 170 nanometers. Slender jets, called spicules, rise and sway there like long grasses in a high wind. They shoot upward at around 100 kilometers per second, hundreds of times the speed of sound in air, and reach heights near 10,000 kilometers, over 6,000 miles. Dwarfing mountains, skimming a measurable fraction of a planetary radius, many form and fade in 5 to 10 minutes. For years, their origin was a puzzle. Charged particles in a plasma are usually tied to magnetic field lines, as if on taut leashes, and seemed too constrained to leap free so abruptly. Detailed modeling, published in 2017, pointed to a quiet helper, neutral atoms, which feel the push and pull of collisions, but are not bound to magnetic lines. As neutrals slide through the ionized gas, they tug on the charged particles, a process often called ion-neutral drift, lending them the slip needed to surge upward and become jets. A small ingredient, easily left out of early models, turned out to be essential to the chromosphere's restless lacework. Below this veil lies the photosphere, the bright layer we casually call the surface. From our distance, its edge looks sharp and well-defined, a clean coin against dark sky. That neatness is a trick of scale. Up close, there is no hard boundary. The sun is plasma through and through, ions and free electrons mingling in the fourth state of matter, the most common state of luminous, ordinary matter in the universe. The photosphere itself is only about 400 kilometers, 250 miles thick, a warm skin, more than a wall, and it is the deepest layer we can measure directly in fine detail, with photons that reach us unimpeded. The granulated pattern, often seen in high-resolution images, thousands upon thousands of bright cells, marks hot gas rising in the centers and cooler gas sinking around the edges, the daily breath of convection on a stellar scale. On that living surface, dark freckles come and go. Sunspots are cooler than their surroundings, but only by comparison. They would still outshine any earthly furnace. Their darkness marks regions where magnetic fields are especially strong. Those fields suppress the usual churning motion that carries heat upward, so energy piles up below and the top looks dim. Compare a visible light view of these spots with an ultraviolet view taken at the same time, and a pattern comes into focus. The most dramatic flares tend to blossom where spots cluster, in places where magnetic energy has been stored, twisted, and set on edge. The sizes vary widely. Some sunspots are small and fleeting, while others grow into complexes up to about 160,000 kilometers, nearly 100,000 miles, across, many times Earth's diameter. Each is a signpost that the field beneath is under stress and ready to rearrange itself. Return for a moment to the idea of color and temperature, because in the sun's atmosphere they are guides to height and heat. Different ions stripped of many electrons, helium with its outer shell missing, shine most strongly at particular temperatures. By tuning instruments to those specific wavelengths, observers pick out layers the way a physician reads different tissues in an imaging scan. Quiet loops, arching between neighboring magnetic footpoints, glow as if traced with a pen. Hotter, denser regions, not with brightness that waxes and wanes. The corona's million-degree glow at 19.3 nanometers shows a broad architecture, while views tuned to higher formation temperatures, the kind that light up during flares, reveal where energy is being stored and spent. The sun's wind deserves a softer, longer look, because its constancy is easy to forget beside the drama of flares. Even when the sun appears quiet, a steady flow of charged particles streams outward in all directions, threading the solar system with a spiraling magnetic field shaped by the sun's rotation. Coronal holes widen those rivers. Active regions can send out swifter gusts. When these flows meet Earth's magnetosphere, they compress and stretch it, and some particles slip down magnetic field lines toward the poles. High in our atmosphere, they bump into oxygen and nitrogen, giving up energy as colored light. On winter nights, the aurora's slow motion can look like kelp turning in a secret tide. On rare, stronger days, the dance steps south, seen from places unaccustomed to such skyfire. Prominences, though grand, have their own tender details. Some are quiescent, resting for weeks or months, balanced between gravity and magnetic lift. Others are eruptive, rising, thinning, and finally letting go. The backbone of a large prominence can be threaded with fine barbs, substructures that form along magnetic channels like beads on a wire. From the side, a filament is a dark smoke line against the bright disk. From the edge, it becomes a bright loop over black space. Coronal rain weaves back through these structures, forming when plasma trapped on long magnetic arches radiates heat, cools, and condenses into denser blobs. These bright droplets trace the field lines as they fall, a kind of weather map written in light. When a coronal mass ejection takes shape, the prelude can be slow. Magnetic fields in the low corona evolve, shearing and twisting around sunspots. A sigmoid and shaped brightness sometimes hints that the system is ready to break. Then the change comes. A loop swells, a cavity appears, and what was rooted lifts away. Instruments watching in multiple wavelengths catch different parts of the story. Cooler material carried along like a scarf. Hotter fronts driven ahead like a bow wave. If the ejection is aimed toward Earth, forecasters track its speed and density to estimate arrival. Most pass with little fuss. A few arrive with enough force to add a line to the history of technology. Telegraph failures in the 19th century, power grid issues in the 20th, satellite disturbances in the 21st. Knowledge does not erase risk, but it turns surprise into expectation and preparation. Timing matters because the sun keeps a rhythm. Over about 11 years, the number of visible sunspots grows and fades. The corona's architecture shifts from simple to elaborate and back again, and the odds of flares and ejections change with the season of the star. At minimum, the magnetic field resembles a tidy dipole, like a bar magnet. At maximum, it is braided and complex, with active regions stepping across each hemisphere in patterns that drift toward the equator. Images taken year after year trace this cycle like rings in a tree, a living record of magnetism rising from within and returning there, transformed. The transition region's sharp temperature jump still invites quiet wonder. Heat moves in many ways: radiation, conduction, convection, and in the sun, each pathway finds its place. Where charged particles trace magnetic fields, conduction carries heat along those axes more readily than across them, and waves launched from below can funnel energy upward with surprising efficiency. The region is thin, but it is not simple. It is where small-scale dynamics open gateways to the corona's million-degree bath. Short-lived brightenings called blinkers and narrow jet-like bursts sparkle and vanish there, brief as the flick of a match. Down in the chromosphere, the orchestra of motion goes on. Spicules are only the most conspicuous players. Fine fibrils lace the surface, tracing low magnetic canopies. Shockwaves, born from the buffeting underneath, ripple outward and upward, sometimes colliding to make bright grains that blink like fireflies. The neutral atoms that help launch spicules also teach a broader lesson. In a plasma, small fractions and subtle couplings can steer the whole. Leave out the neutrals, and the model misses the leap. Add them, and the grass begins to sway. The photosphere's granulation is a comfortingly orderly chaos. Each cell spans about 1,000 kilometers, 600 miles, across. Hot plasma rises in the bright centers, cools, and sinks in darker lanes, only to be replaced by fresh upwells. The cells last minutes before being replaced by neighbors. Superimposed on this texture, larger flows carry heat and magnetic flux across thousands of kilometers, guiding where sunspots will appear and how they will evolve. The magnetic field there does not sit still. It emerges, splits, merges, and submerges, as if the surface were a lake with iron filings, forever drifting to the top and sliding back down again. From this bright skin upward, almost everything we learn comes from light. Spectral lines, the fingerprints of elements, shift, split, and broaden in ways that betray temperature, motion, and magnetic strength. By measuring these changes across the disk and over time, scientists build maps of flows and stresses, reconstructing the invisible scaffolding that guides the visible play. The sun, for all its ferocity, is generous with clues. It helps to gather these threads into a single, gentle picture. Light that reaches an eye on a hillside at dawn began in collisions deep within a core, random walked outward, and finally found a clean line into space. Along the way, it passed through layers where magnetism is king, where heat is guided like water in terraces, where small, uncharged atoms lend slipping room to charged neighbors, where arches lift rivers of plasma as easily as a hand lifts a ribbon. At the edge, great loops hold and sometimes fail, letting matter rain back or drift away. Doors in the halo open and close, shaping winds that comb the planets. The cycle swells and quiets. The orchestra rises and falls. What looks dangerous at first, a flare's sudden bloom, an ejection's broad front, becomes, with patient looking, a pattern we can understand, anticipate, and live alongside. There is no need to rush. The story runs from the gentle bloom of sunrise to the fierce heat beneath it, then back out again to the pale crown that glows during eclipses. Each part answers another. Sunspots, where heat is held back. Flares, where energy is released. Rain, that returns what was lifted. Winds, that carry the sun's touch across space. Instruments, tuned to 19.3 nanometers, show a million-degree architecture. To 30 nanometers, the drama of eruptive days. Around 160 and 170 nanometers, the thin steps between layers and the restless lace of the chromosphere. Invisible light, the mottled skin where we can measure detail most directly. Some weeks, like that lively run in August 2022, the tempo quickens. In quieter seasons, the sun simply breathes. From hilltop to core, from corona to photosphere, the order of things holds. Light, heat, and magnetism intertwined. Understanding does not drain the beauty, it deepens it. A sunrise is still a sunrise, but now it carries the shape of its own making. An old star's labor turned to color, a long journey arriving as a gentle glow. Knowledge, held lightly, is a kind of shelter. It steadies the mind, softens the edges of worry, and lets the night do its work, while a bright engine turns, unhurried, behind the sky. And if that calm invites a closer look, follow it indoors, into the hush beneath a quiet dome, where curiosity becomes a lens. The dark around the observatory is calm, and in that hush, the sun resolves into texture and detail. A pair of similar sunspots comes into view through the Swedish Solar Telescope, using visible light near 400 nanometers. A deep blue our eyes could recognize if we were close enough, and the glare were tamed. Around each spot, the photosphere breaks into jagged, ever-changing tiles, a surface that at first glance looks like cooling lava cracking along fresh seams. Those tiles are solar granules, patches roughly 1,000 kilometers wide, the topmost lips of convection cells rising from below. Each granule is heat, taking the simplest path. Hot plasma wells up at the center and shines brighter because it's hotter. Reaching the photosphere, the sun's thin, visible surface, the flow spreads sideways, shares its energy, and cools. Along the rough, darker lanes between tiles, the cooled plasma sinks, and the cycle begins again. The pattern repeats everywhere. Rise, spread, settle, return. On Earth, convection in the mantle moves continents over ages. On the Sun, convection writes and rewrites the photosphere in minutes. The clock runs fast here. A typical granule lasts around 20 minutes before it's replaced by a neighbor. Yet in that short life, the flow can sprint past 7 kilometers per second. Motion that fast in a compressible medium stirs waves, acoustic ripples, and shock fronts that ring the surface. What looks like fine grain in full-disc photographs at the same blue wavelength is not a camera flaw. It is the granulation itself, the foam of countless cells tiling a globe 1.4 million kilometers across. Once you learn to see it, it's hard to unsee. The sun's daily handwriting. Below this bright layer, light stops carrying a clean picture. The photosphere marks the deepest region we can image directly, because below it, the path outward is too crowded. Photons are trapped and scattered long before escape. Much of what lies beneath is mapped by inference rather than sight. For now, the edge of vision is a luminous skin only a few hundred kilometers thick, resting over a volume so large and active that even a lifetime of watching would feel like peeking through a keyhole. Even that keyhole, opened with care, shows plenty. Using many parts of the spectrum, not just the band our eyes evolved to notice, turns a blinding disk into a layered portrait. Structures that would otherwise remain invisible step forward in ultraviolet and X-ray views. Cooler features announce themselves in infrared. The star is busy with loops, rain, flares, and wind. Much of that bustle would be hidden without these windows. Past the photosphere, the unknowns gather, and one gentle way to reduce their mystery is to consider where the whole story began, because origins steady the mind the way dawn steadies the horizon. Wind the clock back 4.6 billion years to a quiet arm of the Milky Way, where a giant molecular cloud drifted, cold and immense. Such clouds can span hundreds of light years and hold the mass of millions of suns. Hydrogen and helium form the bulk of this reservoir, with grains of dust and traces of heavier elements mixed in carbon, oxygen, nitrogen, iron made long before in older stars. Some of those stars ended as supernovae, throwing their enriched interiors into space. Folded into the cloud, those elements became seeds, ready not only for new stars, but for the rocks, ices, and chemistry that would later build planets. A nudge was needed to make a nest of collapsing pockets from so much serene material. The likely nudge was a shockwave from a nearby supernova, a moving wall of pressure that briefly squeezed parts of the cloud. Squeezed gas can't cool efficiently, and gravity gains the upper hand. Dense regions fragment, gather themselves, and collapse further. Some researchers have even given a name to the hypothetical supernova that may have triggered our portion of the cloud, Kotlikue, after an earth and fertility goddess whose myths fold death into birth. The metaphor fits. In the universe, endings often light beginnings. Collapse does not favor a single giant. Nature prefers many small starts to one enormous one. The reason is an instability described by James Jeans. Inside a cloud, pressure props gas up while gravity tries to pull it together. There is a characteristic size, the Jeans length, at which these tendencies balance. If a patch grows larger than that size, pressure can no longer hold it up. Gravity wins, and the patch collapses. Because density and temperature vary across a giant cloud, some patches cross their threshold sooner than others. Fragmentation follows. Many clumps become many hearts. Each collapsing clump grows into a protostellar core, the earliest stage that looks star-like. Gravity tightens its grip. Gas and dust fall inward, and as they fall, they heat, converting gravitational potential into thermal energy. The core glows from this contraction, not yet from fusion, shining because it is getting denser and hotter. Around it, infalling matter does not simply rain down evenly from every direction. Any small twist is amplified as the region shrinks. Rotation becomes the organizer. Nothing in space is perfectly still, and as a cloud contracts, conservation of angular momentum demands that it spin faster, like a figure skater who pulls in her arms. Near the equator, some of the material's sideways motion is fast enough that it won't fall straight in. It circles instead and settles into orbit. Near the poles, the sideways component is small, and the fall continues more directly. The shape flattens. What began as a puffy, roundish nebula becomes a thin, rotating band girdling a bright center, a protoplanetary disk. That disk is a patient chaos. Dust grains stick, break, and stick again. Ice condenses in the cooler outer zones. Small clumps sweep up neighbors. Large clumps bully medium ones. Some material loses angular momentum through collisions and magnetic braking, and tumbles into the newborn star. Some survives and grows into planets, moons, asteroids, and comets. Over millions of years, a family takes shape not tidy, but durable. Meanwhile, the center gets ready for a change that will last billions of years. A young sun-to-be spends millions of years contracting and heating until its core temperature reaches roughly 10 million degrees Celsius. At that threshold, hydrogen nuclei begin to fuse into helium. Fusion transforms the situation. It isn't only a new source of heat, it is the balance wheel that allows a star to settle. Gravity still presses inward with unbroken patience, trying to shrink the star further. The energy from fusion pushes back. That energy streams outward and creates pressure, thermal pressure from hot particles, and radiation pressure from photons bouncing and scattering. When the outward push matches the inward pull, the star reaches hydrostatic equilibrium. The sun, newly lit, stops contracting and enters the long, steady main sequence, a phase in which the core fuses hydrogen into helium, and the surface shines with nearly constant brightness. This quiet tug-of-war, gravity squeezing in, pressure holding out, will set the rhythm for every chapter of a star's life. It drove the first collapse, defines the present calm, and one distant day will shape the ending. The details of fusion are the heart of the matter. The sun's core runs near 15 million degrees Celsius. The pressure there is more than 250 billion times Earth's sea level air pressure. Hydrogen atoms are stripped into a plasma of free protons and electrons, electrically charged and constantly colliding. Charges matter because, like charges, repel. Protons push protons away via the Coulomb force, the same principle that keeps the like poles of two magnets from meeting. To fuse, two protons must get unimaginably close, close enough for a different interaction, the strong nuclear force, to take hold and bind them. The strong force is powerful, but it acts only across distances comparable to a proton's size, about a femtometer, 10 to the power of -15 meters. At larger separations, Coulomb repulsion rules. Classically, this looks impossible. Early 20th century calculations using only the rules of everyday particles and smooth forces, suggested that the sun's core wasn't nearly hot enough to let protons climb the Coulomb barrier. By that reasoning, fusion would require billions of degrees. The sun, steady and bright, made a quiet joke of those numbers. Something in the model had to widen. Quantum mechanics provided the widening. In that framework, particles behave as both localized points and spread out waves. A wave can seep into places a classical particle could never reach. This seepage is quantum tunneling. Instead of climbing over an energy barrier, a particle has a small chance of being found on the other side, with no classical path in between. The chance isn't large, but it doesn't have to be. In the core, with countless protons moving quickly and for a very long time, rare events add up to a steady current. Picture the Coulomb barrier as a hill between two valleys. A classical traveler needs enough energy to crest the hill. A quantum traveler has a tiny chance to appear in the second valley without standing on the summit. In the sun's core, that tiny chance is enough. A small fraction of proton-proton encounters tunnel through the barrier and come close enough for the strong force to snap on over femtometer distances. When it does, binding begins, and with it, a chain of reactions that turn mass into energy with exquisite efficiency. The dominant chain in the sun is called the proton-proton chain. Its first step is subtle and slow. Two protons combine, and through the weak interaction, transform into deuterium, a nucleus with one proton and one neutron, while emitting a positron, the electron's antimatter, twin, and an electron neutrino. The weak interaction lives up to its name, and that slowness is a gift. It stretches the sun's fuel across billions of years. Once deuterium exists, it quickly captures another proton to form helium-3 and releases a gamma-ray photon. Finally, two helium-3 nuclei fuse to make helium-4, a tightly bound nucleus of two protons and two neutrons, and two free protons are returned to the pool. Each completed chain releases energy that, after a long, scattering journey outward, becomes the sunlight on a morning window. Nearly all of the sun's luminosity comes from this pathway, about 99%. There is another route that matters more at higher temperatures and in more massive stars, the CNO cycle, named for carbon, nitrogen, and oxygen, which act as catalysts. In that cycle, a carbon nucleus captures a proton and becomes nitrogen. Nitrogen captures another and becomes oxygen. Along the way, positrons and neutrinos are emitted, and gamma rays carry off energy. The sequence returns to carbon after fusing 4 protons into one helium nucleus. The CNO cycle grows more efficient as temperature rises. In the sun, it contributes a small fraction, a soft harmony under the proton-proton chain's steady melody. All of this power takes the long way out. A gamma ray born in the core ricochets endlessly, scattering and sharing energy, until after hundreds of thousands of years, its energy has been divided among many lower energy photons. Some of those finally walk unhindered through the photosphere and fly free. By the time that energy warms a face at sunrise, the individual photon is a descendant, the many times removed child of a gamma ray that began its life when landscapes on Earth were different. At the surface, by contrast, the patterns we watch: granules brightening and dimming, lanes darkening and clearing last minutes, short above, long below, and both steady. The granulation around a sunspot adds another layer to the picture. In the darkest core, the umbra magnetic fields are strong enough to suppress normal upwelling, so the region looks cooler and dimmer. Around it, the penumbra forms a gray fringe braided with filaments. channels where plasma flows along tilted magnetic lines. The shapes of nearby granules stretch and skew under those fields. Above, loops reach into higher layers and may later guide prominences or shape coronal rain. Everywhere, motion and field converse. The resemblance to cooling lava is tempting but incomplete. Lava crusts and cracks because the surface cools and stiffens over a viscous interior. The sun's skin is not a crust over a solid heart. It is the thinnest atmospheric layer above a convection zone so vast that a single cell would swallow continents. The jagged edges we see are not fractures, but lanes of returning flow. The entire surface is a simmer, maintained by an engine below, with heat continually finding paths upward, outward, and back down again. When a full disk image appears noisy or over-textured, it helps to remember what you're actually seeing. Spacecraft and ground telescopes that resolve well enough show the same foam in detail. Instruments that can't resolve it still hint at the texture as a fine mist. The granulation is the signal. It is proof that ordinary rules, hot material rises, cool material sinks, hold even on a star. This, in the end, is the comfort behind the danger. The sun can surprise us with storms when its magnetic temper flares, yet it is also law-abiding in ways that help us rest. Convection cells rise and fall by the same physics that rolls boiling water. Magnetic fields twist and store energy by the same equations that turn a compass needle scaled up to celestial size. A cloud begins to collapse when gravity wins a simple contest with pressure by a margin a pencil can compute. Fusion proceeds because the universe allows particles to behave as waves, giving them a chance to tunnel through barriers too tall to climb. In such a universe, a human on a mountain can point a telescope at one color 400 nanometers and watch the topmost ripples of a deep, orderly sea. The photograph of two sunspots is a quiet crossroads. Around the dark cores, granules jostle and pour. In the penumbra, fine filaments sketch paths where plasma slides along tilted magnetic fields. Above, arches lift into the chromosphere, and corona, guiding matter upward and letting it fall again as shining rain. Beyond that, magnetic doors in the halo open and close, shaping winds that sweep the planets and sometimes brush our skies with color. Far behind it all lingers the memory of a giant cloud and a shock that made pockets collapse, a tale some link to Coatlicue, the goddess whose stories remember that death feeds life, and the mathematics that says many small parts, properly arranged, can become a star. Deeper still, in a furnace no photograph can show, two protons tunnel and meet. The strong force catches, a chain begins, a photon is born. Patience carries that photon to the surface, and greater patience bears it across space to an eye on a hill. The light arrives without hurry. The granules flicker, the spots evolve. The star holds its balance and invites us to follow the brightness back to its source. Energy in the sun begins as a small loss that becomes a great gain. In each fusion step, a sliver of mass becomes energy, just as Einstein's E equals mc squared promises. 4 free protons do not weigh as much as the helium-4 nucleus they form. The helium is lighter by a whisper of mass, and that missing amount reappears as heat and light spreading outward through the star. Every second, the sun turns roughly 4.3 million tons of itself into radiance millions of cars' worth of mass, transformed in an instant. That steady burn lights mornings and warms oceans, drives weather and photosynthesis, and threads the solar system with illumination, the quiet answer to the picture of spots and loops above. the deep engine whose work becomes dawn. The energy does not leap from the core to space in a single bound. Above the region where fusion happens lies about 700,000 kilometers of solar interior, and a photon born in the furnace must thread that depth before it can fly free. To feel the complexity, follow a single photon from its first moment in a proton-proton reaction to the edge we see as the surface. The path is not smooth. The photon's journey is a long meander through layered terrain, a patient drift rather than a dash. It begins in the core, a sphere that occupies roughly the inner quarter of the sun's radius and carries nearly half its mass. The core is dense, about 160 grams per cubic centimeter, more than 20 times denser than iron. If a smartphone were made of such stuff, it would weigh like a sledgehammer. In that crush, our photon can't travel far before it slams into a neighbor and is absorbed. The neighbor soon re-emits a photon, but not necessarily in the same direction or with the same energy. The new photon careens a short distance, meets another particle, vanishes into it, and emerges again somewhere else, aimed by chance. Step, bump, turn. Step, bump, turn. The motion resembles a random walk, like Brownian motion, the jittering of specks in water when jostled by invisible molecules. There is no preferred direction. A photon can spend ages trending outward, only to be thrown inward by a single collision. The long shuffle changes the photon's character. Deep in the core, it tends to be a gamma ray, a very high-energy packet of light. With each absorption and re-emission, some of that energy is shared with the plasma. Across countless interactions, the average energy declines. Gamma rays soften into X-rays. X-rays mellow toward ultraviolet. And by the time the pack finally reaches layers near the surface, many photons have energies in the visible band. The light that touches a window pane began life as something far fiercer and was gentled by a crowd. We cannot open a window into the core with light of any kind. The outer layers make a perfect curtain for that view. Instead, to probe the hidden engine, scientists lean on indirect senses and the faithful logic of models tested against what can be seen. One such sense is helioseismology, the study of waves that ruffle the sun's surface. Sound waves generated by the churning below run through the interior, turn, and return to the visible skin. Their timing and pattern depend on the temperatures, densities, and motions inside. By watching tiny ripples in brightness and motion on the surface, oscillations measured with exquisite precision, researchers can infer how fast sound travels at different depths and reconstruct the structure beneath. Much as seismologists map Earth's interior with earthquake waves, another messenger slips through almost unimpeded: the solar neutrino, born alongside the first step of the proton-proton chain. Neutrinos interact so weakly with matter that they fly out of the sun in about 2 seconds, ignore the chaotic maze that traps photons, and head into space at nearly light speed. Early detectors on Earth counted fewer solar neutrinos than theory predicted, a mismatch that worried both solar physics and particle physics. The riddle was solved when experiments showed that neutrinos change flavor as they travel, oscillating among electron, muon, and tau types. Detectors that could see only one flavor had been missing the others. With that discovery, the counts matched, and confidence in both the sun's fusion engine and the quantum nature of the neutrino deepened. Past the core edge, our photon enters the radiative zone, which stretches outward to about 70% of the sun's radius. Temperatures there fall from around 15 million degrees Celsius at the base to something like 2 million near the top. The density also falls, comparable to heavy metals deep down. dropping to less than that of liquid water higher up. Radiation remains the main way energy leaks outward. Photons hop from particle to particle, step by tiny step, on average drifting toward the surface. Even so, the material is astonishingly opaque. A few centimeters of solar plasma in this zone can block as much light as hundreds of meters of water. Motion through such stuff is not so much travel as it is diffusion. Our picture of this region rests on a framework called the Standard Solar Model, SSM, built from the principles of hydrostatic equilibrium, pressure balancing gravity, energy conservation, and radiative transfer. The model uses laboratory-tested physics, how gases behave at different temperatures and densities, how radiation scatters and is absorbed to calculate opacities, how transparent the material is to light at each depth. From those opacities and the need to carry the star's energy outward, the model finds temperature and density profiles and identifies where radiative transport becomes inefficient and another method must take over. Mathematics, in this setting, becomes a vessel for exploration, allowing us to map rooms we cannot enter, the same way quantum mechanics lets protons cross a barrier they could not classically climb. Near the top of the radiative zone lies a thin, strange frontier, the tachocline. Here the organized, slowly varying flows of the radiative region meet the turbulent churning of the layer above. The sheer differences in rotation speed with latitude and depth seems to be sharp in this transitional band. Many lines of evidence suggest the tachocline plays a central role in the solar dynamo, the process that builds and maintains the sun's magnetic field. Fields are twisted and amplified here, seeds of the loops and knots that will later rise to the surface as sunspots and eruptive regions. The layer is thin in radius but large in consequence, a quiet fulcrum for storms we will eventually see. Above the tachocline, the convective zone takes over, extending to just beneath the visible surface. Temperatures have fallen below about 2 million degrees Celsius, and the plasma becomes too opaque for radiation to move energy efficiently. Heat finds a quicker path by moving matter. Hot plasma rises in vast buoyant cells. Cooler plasma sinks in the lanes between. The motion is familiar in spirit, like water boiling in a pot, but colossal in scale. The rising cells we can see at the surface are granules, thousands of kilometers across. Their upflows can reach hundreds of meters per second. Push a beach ball underwater and feel it strain to pop up. That desire to rise is buoyancy. On the sun, buoyancy moves enough mass to dwarf metaphors. The power involved has been likened to billions of hurricanes operating at once. Convection carries energy to the surface far more efficiently here than radiation could, setting up a rolling, turbulent sea of plasma. The change in transport is not absolute. Photons still scatter and carry energy, but the bulk of the work is now done by motion of matter rather than by radiative diffusion. As rising plumes reach the top of the convective zone, they spread and cool. Sinking flows gather in the dark lanes, and the cycle repeats. In this dance, our photon rides along, swept upward by moving plasma, until it reaches the layer from which escape is finally possible. That layer is the photosphere, the thin band we perceive as the sun's surface. By this height, the temperature has fallen to about 5,500 degrees Celsius. The plasma has thinned enough that a photon has a reasonable chance of flying outward without immediately being reabsorbed. The photosphere is only a few hundred to roughly 500 kilometers deep, a skin, not a crust, and most of the sunlight we see is emitted from this narrow shell. Above lies the low-density atmosphere, chromosphere, and corona. With the corona's density only about a billionth of the photosphere's, it is tenuous enough to barely hinder outbound light. From here, our photon departs at light speed, crossing the 150 million kilometers to Earth in about 8 minutes, while its neutrino cousin, born at the same moment deep inside, has already been roaming interplanetary space for ages on human timescales. Fusion does more than power the present. It slowly reshapes the star. In the core, hydrogen is converted to helium, and helium ash accumulates. Helium is more massive per nucleus than hydrogen and does not fuse at the Sun's current core conditions. As the helium fraction grows, the core becomes denser. Because the helium-rich regions produce less energy per unit mass at the same temperature, the outward push of pressure weakens relative to gravity. Gravity responds by squeezing harder, and the core contracts. Compression heats it further. Fusion rates are exquisitely sensitive to temperature, so a slightly hotter core burns hydrogen faster, releasing more energy and boosting the outward pressure. Balance is restored at a higher luminosity. Through this feedback loop, the Sun has brightened by roughly 30% since it first settled onto the main sequence, and it will continue to brighten for billions of years as long as hydrogen fusion dominates in the center. These changes ripple through the layers. Higher core temperatures generate more energetic photons, which interact more strongly with the surrounding plasma, increasing opacity in the inner radiative zone and lengthening the time energy spends trapped there. The region over which convection is the most efficient carrier of heat can expand slightly as the energy flux grows. The outer layers adjust their temperatures and densities to maintain hydrostatic equilibrium. Nothing in the star is static. Everything is responsive, even as the whole appears steady to our eyes. Project the story forward, and a different kind of balance appears on the horizon. In roughly 5 billion years, the core hydrogen supply will be largely exhausted. Fusion will proceed in a shell surrounding an inert helium core. The core, lacking energy generation of its own, will contract and heat. The outer layers will respond by expanding and cooling. The Sun will swell into a red giant, its radius ballooning so much that Mercury and Venus will be engulfed and the inner system remade. Whether Earth is swallowed or merely scorched into an airless ember depends on the complicated exchange of mass and angular momentum as the star expands, but the neighborhood will be unrecognizable either way. As the core's temperature rises during contraction, it eventually reaches a threshold where helium can fuse. In a sun-like star, the onset is rapid, a helium flash, after which the core settles into a new balance, burning helium into carbon and oxygen. The outer layers adjust again, and the red giant phase evolves. When the helium is spent, fusion can no longer find a path in the Sun's modest mass. The outer layers will be shed into space, forming a glowing shell, a planetary nebula lit from within by the remaining hot core. That core, no longer a fusion engine, will cool over eons as a white dwarf, Earth-sized, carbon-oxygen-rich, and extraordinarily dense, an ember that remembers a long fire. The road from core to surface, from birth cloud to white dwarf, is drawn by a few reliable rules. Mass becomes energy in tiny fractions that add up. Photons do not stream, they wander. Waves on the surface echo the shape of the rooms below. Neutrinos ghost through walls and bring news. Where radiation can no longer keep pace, matter moves and carries the heat instead. A thin layer lets light go. Composition changes, and the balance shifts, and the whole brightens. Gravity pulls, pressure answers. The star breathes into a new phase. None of this negates the sun's temper flares, ejections, and winds that can unsettle our machines and paint our skies, but all of it makes the temper legible. A single number like E equals mc squared can feel too neat for such a sprawling story, yet it sits quietly at the root of every step. The missing mass in helium-4 fuels the glow that starts the photon we followed. The glow is delayed by a maze, yet arrives in time to warm a winter morning. The maze is mapped by equations we can test, and by ripples we can measure, and by particles we can count, underground in pools of silent water. The brightness grows as the core changes. The surface pattern shifts without losing its calm. A hot wind threads the planets, and a thin crown shines in eclipses. Far away, the future waits with its red swell and its pale remnant. Let the mind drift a little while it holds these pieces that drift belongs to the learning. The sun is fiercer than we guessed, because magnetism hoards energy in restless knots that sometimes reach us. It's also more knowable because the same clean laws stitch small scales to large. A photon wanders for ages, then crosses space in a breath. A neutrino leaves at once and whispers that the core is alive. Granules tile the skin. The tachocline winds the dynamo. The radiative zone quiets the light until convection lifts it. The photosphere lets it go. The core brightens with time. The finale will be grand, then gentle. Between those bookends, the star keeps time, and knowing that beat is its own kind of hush. That beat doesn't stay in the sky. Much of the sun's work is invisible to us, yet its rhythm, rising and falling, pulses of magnetism and light, runs through our neighborhood and tugs on earthly things. It isn't prophecy, it's physics. In a lively year, like 2025, that background tempo leans warmer and clearer in some places, makes our technology a touch more temperamental, and leaves faint biological ripples you only notice across vast ledgers of lives. A quiet metronome overhead, and down here, the world sways by a hair. The sun looks serene to a casual glance. It rises, it sets, and the day behaves. Beneath that calm is a restless sea of plasma. The surface churns with granules that form and vanish in minutes. Darker patches, sunspots open, where magnetic fields are strongest, sometimes no bigger than a tiny continent, sometimes sprawling across 160,000 kilometers, great islands of suppressed heat. Above, loops rise into the chromosphere and corona. Some loops snap, throwing a burst of radiation called a flare. Some unravel and fling matter into space as a coronal mass ejection. The corona itself bakes at temperatures hundreds of times hotter than the photosphere, a long-standing puzzle and a sign that magnetic energy is being turned into heat in fierce, efficient ways. All this motion follows a rhythm. About every 11 years, the sun's activity swells to a maximum and then quiets to a minimum. This Schwabe cycle shows up in counts of sunspots and in tallies of flares and eruptions. During a quiet year, a large flare is rare. During an active year, you might see many in a day. The magnetic roots run deeper. Every 11 years, the polar magnetic fields flip, north becomes south, and south becomes north, and then, after another 11, they flip back. This longer rhythm, the Hale cycle, runs at 22 years and turns the sun's heartbeat into a full magnetic breath. In, out, repeat. The cycle's exact length wanders. We've watched its mood for 2 centuries. Ice cores and tree rings hint at its fingerprints across 10,000 years. Why 11? We don't fully know. The internal dynamo that braids and drags field lines likely sets the pace. Some have pointed to Jupiter's 11-ish year orbit as a possible metronome, since the giant planet tugs on the Sun as both bodies move around their shared center of mass. The match in timing may be coincidence. Jupiter's pull can't explain the cycle's irregularities. For now, the rhythm is a measured mystery we can count and prepare for, even if we can't yet derive it from first principles. Preparation matters, because space is part of our infrastructure now. Solar storms, geomagnetic disturbances, driven by fast streams and mass ejections, travel outward and, if properly aimed, brush Earth's magnetic field. Days beforehand, spacecraft watching the Sun can spot the flare or ejection. Hours beforehand, satellites stationed between Earth and Sun measure the approaching wind and alert forecasters. Astronauts take shelter when radiation spikes. Operators power down sensitive instruments on satellites to avoid electrical surges induced by energetic particles. A strong storm can pump extra current into long wires, nudge spacecraft electronics into glitches, and flip bits in memory. It can also change the air itself. High above, the atmosphere is thin but not absent. When energetic particles pour in, they add heat. Warm air expands, and the upper atmosphere puffs outward. The change is gentle to the touch and dramatic to an object moving at orbital speed. Satellites in low Earth orbit normally nudge themselves a few times a year to counter tiny drag. During stormy months, they may need to maneuver every couple of weeks. Now and then, a sudden blossom of air resistance hastens a satellite's re-entry. In 1989, an especially strong event helped end a solar observatory's time in orbit ahead of schedule. After big storms, tracking networks must update the paths of hundreds of satellites whose orbits have been tugged into new shapes. The sky grows busier and more fussy when the Sun is loud. The ionosphere, the region where sunlight knocks electrons free and turns air into a conductive plasma, also changes with space weather. Extra ionization bends radio waves differently, which can blur satellite navigation. A positioning error that would normally be under a meter might swell to 10 meters or more, confusing maps and guidance for a while. Long-distance radio can improve, though. Pilots and amateur operators use the charged layers as mirrors, skipping signals beyond the horizon. Power grids brace for geomagnetically induced currents, with better grounding and careful load management. None of this is apocalyptic. It is the practical dance of a technological civilization living under a variable star. The bright side is literally bright. As the solar wind strengthens and the magnetosphere flexes, auroras spill farther from the poles. Places used to a few quiet nights a year may see curtains of green and red twice a month during the most excitable stretches. Travelers plan by the Sun's rhythm. Photographers watch forecasts the way sailors watch tides. The sky remembers to be theatrical. The surprises are not limited to machines and lights. Biology pays attention to small changes, often without a conscious note from us. At solar minimum, the Sun's magnetic outflow weakens, and our heliosphere, the vast bubble of solar wind that envelops the planets, offers less shielding against cosmic rays from deep space. Those particles rarely make it to the ground, but they reach the upper atmosphere easily and can trigger chains of reactions. One long-debated idea is that increased cosmic rays can seed extra cloud droplets by providing nucleation sites, slightly changing cloudiness. The evidence is mixed, and the effect, if real, is subtle. What's clearer is that during solar maximum, energy pouring into the upper atmosphere and ocean atmosphere system can nudge global temperatures a little higher for a while. The bump is small fractions of a degree, and it fades as the cycle turns. But small changes can matter to creatures tuned to seasonal cues. Birds notice. Warmer springs encourage some species to lay earlier. A study of blue tits in the Netherlands reported that laying times across several nesting groups shifted in ways that correlated with sunspot numbers. A curious result even the authors treated with care. Birds don't count spots. They respond to temperature, daylight, and food. The sun's cycle may be threading through those cues. Other animals tune to magnetism. Homing pigeons, for example, adjust routes and reliability depending on the state of the geomagnetic field. Migration is a suite of senses working together, and one of those senses is the sky's magnetic fabric, which the sun stretches and relaxes. Humans are not exempt from small correlations. When researchers look across very large populations, faint patterns sometimes appear. A long study in the Netherlands, following a large fraction of the female population, reported peaks in several cervical pathologies shortly after solar maxima, when radiation and geomagnetic activity run high. The same project noted that a tracked man showed small rises in oral temperature, pulse, blood pressure, and respiration after peaks in the cycle. Another analysis of hundreds of thousands of records in a state medical database found that people born during more turbulent solar years had slightly higher rates of certain mental health diagnoses later in life. These findings are statistical whispers, not clinical thunderclaps. They don't tell you what will happen to a particular person. The effect sizes are tiny. Researchers emphasize how many records were needed before any signal emerged, and they debate causes. Are we seeing biological responses to light and magnetism? Secondary effects from weather? Artifacts in data? The work continues. If small drifts in mood and illness risk can be found, small uplifts may be found too. Some studies hint that turbulent solar years correlate with bumps in creativity and adaptive behavior. It's tempting to weave a tale that a long ago maximum nudged human brains toward abstraction and self-awareness. That is a poetic conjecture, not a settled fact. Yet, it captures a deeper point. Change, even when slight, may stir capacities as well as costs. The same star that can unsettle a satellite can also paint a sky and set a mind wandering. None of these biological threads imply cosmic destiny. They describe gentle tilts in averages, not commands. The sun's cycles should not govern our choices. They simply exist as a background rhythm that sometimes syncs with rhythms closer to home. If you were to write this as a horoscope, it would read oddly practical. Expect a few glitches in communication systems, a better chance of night displays in the north, a mild nudge in seasonal timing, a whisper of health statistics heard only across crowds, and perhaps a fractional uptick in surprise and invention. Behind these influences is a simple fact about protection. When the solar wind is strong, its magnetic field drapes around Earth's own, creating a layered shield that deflects some high-energy particles from beyond the solar system. When the solar wind weakens, that shield slackens, and more cosmic rays can reach the upper air. Chemistry there is sensitive. Ionization cascades alter how molecules cluster and break apart. The path from those changes to cloud cover, rainfall, or temperature is long and full of forks, which is why the signs remain faint. But it's enough to keep scientists curious and cautious at once. Curiosity is being given new tools. 2 missions now fly close enough to taste the solar wind and smell the edge of the corona. One loops deep into the inner heliosphere, skimming close to the sun to sample magnetic fields and particles where they are made. The other rides higher and asks for wide views and razor-sharp measurements of the poles and far side. Between them, we are starting to see how the magnetic carpet at the surface braids into the million-degree crown above, where the wind accelerates, and how the dynamo's slow, deep turn appears as daily weather in light. These spacecraft shrink ignorance the way dawn shrinks shadow, not all at once, but in definite steps. Meanwhile, the present cycle ticks on. The current maximum has already flexed muscles we hadn't seen in years, and the tally of flares and eruptions rises and falls like surf. Technology companies schedule updates with the forecasts in mind. Power operators run drills. Airlines adjust routes when polar radio becomes patchy. Photographers in mid-latitudes glance at indices and then at the sky. This is the ordinary work of living near a star. Plan for its moods, enjoy its gifts, learn its patterns. None of this asks for anxiety at bedtime. It asks for perspective. The sun is more dangerous than we once imagined, because we rely more than ever on machines that notice its storms, and because we've learned how to measure hazards that once passed unremarked. It is also more dependable than fear allows. Its cycles hold within a narrow band. Its storms come with signs. Its long-term brightening is slow enough for geologic thought. For a listener dozing in the dark, the practical translation is simple. Your devices may hiccup. The aurora might wander south. Spring may arrive a whisper early somewhere. A handful of studies may log tiny drifts in health data. And above it all, the sun will keep a beat that we can neither ignore nor fully hear. Think of the cycle as a metronome in another room. Now and then the rhythm lines up with the song you're playing. Most of the time, it just keeps time. Machines and animals that care about timing sometimes catch the beat. The rest of us mostly notice the light. We don't need to assign omens to the clock. We only need to know it's there. The warmth that makes clouds and crops owes nothing to prophecy, but the pulse that occasionally ripples our maps and our skies is worth learning by heart. Learning it makes us better pilots, better planners, and, in a quiet way, better dreamers. Let your thoughts wander. A little drifting is part of learning. The sun is harsher than we once imagined, because magnetism knots energy, and, when it slips, the release can find us. Yet it's also more legible than we feared. The same simple laws stitch the tiniest scales to the grandest. A photon random walks for ages, then crosses space in a breath. A neutrino escapes at once, and quietly proves the core is alive. Granules tile the skin. The tachocline winds the dynamo. The radiative zone hushes the light until convection lifts it, and the photosphere lets it go. The core brightens with time. The ending will be grand, then quiet. Between those bookends, the star keeps time, and knowing the beat becomes its own kind of hush. That beat doesn't stay aloft. Much of the sun's work is unseen, yet its rhythm rising and falling pulses of magnetism and light threads through our neighborhood and nudges earthly things. Not prophecy, just physics. In a lively year like 2025, the background tempo leans warmer and a touch clearer. In some regions, turns technology a bit more temperamental and leaves faint biological ripples you only notice across vast ledgers of lives. A steady metronome overhead. Down here, the world sways by a hair. Survival demands a shield, and Parker carries one like a knight's buckler, always between itself and the star. It's an 11-centimeter carbon composite slab with a white, reflective face to bounce away as much heat as possible. The probe flies, shield first, keeping that round wall perfectly aligned to the sun, while instruments peek and sip from the shadow it casts. Pointing isn't negotiable. If the spacecraft were to expose its body directly to the solar glare, delicate systems would cook in moments. Because the shield must stay pointed at the sun, the high-gain antenna can't always point at Earth. Communications drop out for long stretches, and the craft has to think for itself. Run the sensors, set and adjust exposure, choose what to store at full resolution, compress what can be compressed, and hold its breath until geometry and safety allow a transmission window. Autonomy here isn't a luxury. It is the only way to come home with a record of what was seen. A second emissary follows a higher, cooler track. ESA's Solar Orbiter began development in 2012 and launched on the 10th of February 2020, atop an Atlas V. Like Parker, it leaned on celestial handshakes, gravity assists from Venus and Earth, to settle into an initial orbit that loops around the Sun in about 180 days. Closest approach comes roughly every 6 months at about 43 million kilometers. That distance sounds generous beside Parker's Daredevil passes, but sunlight there is still 13 times stronger than at Earth, and exposed surfaces would fry at around 500 degrees Celsius, 932 degrees Fahrenheit. Solar Orbiter wears a different kind of armor, a multi-layer heat shield, including titanium foil sandwiches, nearly 40 centimeters thick in all, pocked with feed-throughs so telescopes can look out, while the rest of the spacecraft stays tucked in the shade. It is less extreme than Parker's shield, because it doesn't have to be. The mission trades some proximity for a broader set of eyes. Both missions chase related questions. How does the corona reach temperatures of 1,000,000 degrees and beyond, when the surface below sits near 5,500 degrees Celsius? Where and how do the fast and slow solar winds start? What magnetic structures cradle flares and give birth to coronal mass ejections? How is the Sun's global magnetic field built from the tangled threads at small scales? And how does that field flip every 11 years? Parker flies into the wind and samples it as it forms, catching particles, electric fields, and magnetic knots in the act. Solar Orbiter steps back just enough to carry both particle detectors and an imaging suite, telescopes that can take close-ups of a region, then come back again and again to watch it change for days. One sips the soup, the other films the pot. The wind is often a constant murmur, but reconnection, the sudden rearrangement of magnetic field lines, can hurl matter and energy outward in an instant. When a large coronal mass ejection, or CME, is lofted in our direction, it can trigger a geomagnetic storm as it couples with Earth's magnetosphere. The strongest storms are rare. The most famous, in the mid-19th century, is still the yardstick. In late August 1859, sunspots bloomed in a single active region. On August 29, auroras shone far from their usual polar haunts, a sign that space weather was already unsettled. Near midday on September 1, two observers, Richard Carrington and Richard Hodgson, watched an intense white light flare, sketched it, and wrote careful descriptions that later appeared in journals. The flare was tied to a CME that reached Earth in roughly 17.6 hours, far faster than the usual 2 to 3 days. One likely reason is that an earlier ejection had plowed through the inner heliosphere on August 29, clearing out slow solar wind and leaving a rarefied slipstream. With less to push against, the main blast raced ahead. On September 1-2, the largest geomagnetic storm ever recorded unfolded. The sky rippled with color over the Caribbean and Hawaii, across Mexico, northern Africa, and down into the southern hemisphere. Auroras glowed at latitudes that almost never see them. In the Rockies, miners woke to green light and began making breakfast, fooled by a false dawn bright enough to read by. Beauty had a sharp edge. Telegraph systems across Europe and North America misbehaved as induced currents surged through long wires. Operators reported shocks, sparks arced from hardware, and yet some lines kept sending messages, even with power supplies disconnected. The storm's currents were enough to drive the circuits. Earth's magnetic shield had been hammered and compressed deep into the upper atmosphere. The long conductors we had strung across continents became accidental antennas, soaking up energy from above. The decades since have seen strong storms, none on that scale. In March 1989, a CME jolted satellites, knocked radio off balance, and tripped protective relays in Quebec. A large swath of the grid went dark for hours. Lights came back, and lessons were learned. We built better shields, installed monitors, and wrote playbooks. Even so, a storm of Carrington class in the present day would be a different kind of test. In 1859, the world's electrical network was a toddler. Now it is the spine of civilization. Long transmission lines, large transformers, and global fiber routes knit continents together. Satellites hold up navigation, timing, weather, imaging, finance, and communications. The systems most at risk are those that stretch the farthest and carry the largest loads, grids, and undersea cables, because long conductors pick up more of the storm-driven electric fields. Without sensible safeguards, a severe hit could damage transformers in ways that take time to repair. Many of those units are custom-built and heavy. Manufacturing and delivery can stretch to months or years. A long outage cascades. Refrigeration fails. Fuel pumps stall. Payment systems blink. Networks fragment. Hospitals run on generators and then juggle priorities when the fuel runs thin. None of this is inevitable. It is what planners prepare against. Estimates of potential economic costs have climbed into the trillions of dollars for a worst-case U.S. scenario. The more dire projections, multi-year recovery, widespread hardship describe extremes that authorities work actively to avoid, with staging, spares, and procedures. The point isn't to cultivate dread, it's to respect the hazard and lower the odds. Speed is part of the challenge. A fast CME can cover the Sun.Earth distance in under a day. The good news is that the Sun telegraphs intent. Imagers see the launch, coronagraphs watch the cloud expand, and spacecraft stationed sunward sample the approaching wind hours before it arrives. With enough eyes in the right places, operators can harden systems and ride out the blow with less damage. In July 2012, a Carrington-scale event erupted in a direction that missed Earth by roughly 9 days of orbital motion. Luck isn't a plan, so we keep building a better forecast. Side by side, the two missions describe complementary virtues. Parker's closeness grants access to regions where the solar wind is still becoming itself. Its instruments aren't built to stare at the brilliant disk. No camera can look directly at the sun from that distance and survive. Instead, it carries particle counters, electric field and magnetic field sensors, and a white light imager that reads the wind by looking sideways into space. It measures the sizes of turbulent eddies, the shapes of electric and magnetic fluctuations, the feast and famine of particles energized by nearby reconnection. Solar Orbiter, a little farther out, brings a richer palette of eyes. It images the surface and atmosphere at multiple wavelengths, extreme ultraviolet for hot arches and foot points, visible light for granulation and spots, coronagraph views to track CMEs as they detach and swell. Because it can hover over a region as the sun turns, it stitches together time-lapse stories. The slow build of a filament, the simmer before a flare, the birth of a wind stream from a coronal hole. One mission drinks the soup and tells you how it tastes. The other shows you the ladle as it stirs. The common thread is a magnetic star. The corona's million-degree heat, the solar wind's speed, the flare's sudden glare, the ejection's mass and momentum, each is a manifestation of fields braided, twisted, and reconnected. Parker has already flown through patches where the magnetic field flips back on itself, switchbacks, and found fine-scale structure in the wind near its roots. Solar Orbiter has imaged tiny campfires in the low corona, small brightenings that may be the fingerprints of heating events happening all the time. Too small to notice from Earth, but abundant enough to matter. Tie the in situ measurements to the images, and the picture sharpens, where the field opens to space, where it closes back on itself, where the wind is fast, where it is slow, how a small change in the foot points can ripple outward into a gale that arrives at Earth days later. The practical reasons for caring are plain. Better maps of the sun's magnetic surface lead to better models of the wind and its embedded fields. Better models lead to better arrival time estimates, better warnings for astronauts and airlines, better grid management, better satellite operations. The deeper reason is older. We live next to a star, and this is what a star's like up close. Not a perfect lamp, but a living electromagnetic machine whose moods we can learn. The knowledge allows gentler nights. A forecast that says, minor storm tells an engineer to expect a small shift in ionospheric delay, and tells a family in Wisconsin that the northern lights might come calling after dinner. The Carrington story remains a cautionary lantern, held up to show how strong a storm can be. The Quebec blackout, a reminder that the modern world is laced with long wires that need careful watching. The near miss in 2012, a reminder that chance is not the same as safety. Threaded through is a sense of proportionality. Most storms are modest. Most days, the wind is kind. The same sun that can stir wires also grows crops and lights windows. Planning is not fear. It is respect. Back at the edge of the corona, the two spacecraft continue their rhythms. Parker slips behind its shield, instruments tasting torrents of ions and electrons, watching the magnetic field turn and kink in ways models only guessed at before. Solar Orbiter turns its telescopes toward a patch of active region and watches it evolve hour by hour, looking for the telltale shifts that precede a flare or the sag that precedes an eruption. Together they close the loop between cause and effect, a field-line footpoint that drifts, a loop that brightens, a switchback that flips, a gust that leaves the sun and is later felt by a sensor, and finally by a magnetometer in northern latitudes as the sky begins to move. In that loop is the quiet promise of better days. Warnings come earlier, models err less, operators sleep easier. The corona's heat stops being a paradox and becomes a balance sheet of countless tiny bursts. The wind's variations stop being a nuisance and become a pattern we can forecast like a tide. Flares and ejections stop being jump scares and start being events with signatures we can read and messages we can pass along. The metronome keeps its beat strong, one decade, soft the next, and our instruments keep time. There is a tenderness in the engineering, too. A carbon disc that always faces the blaze. A titanium quilt that lets a telescope peek without melting. a software brain that keeps a spacecraft safe when no one can speak to it for days, a camera shutter that closes itself in time with a wobble to avoid a direct, lethal glare. They are acts of care from a small species that understands just enough to send messengers to the edge of danger and bring them home. Even the worst-case thinking has a gentler purpose. It is there to guide what to harden, where to add a valve or a switch, which spares to stock, what drills to run. It lives alongside the joy of auroras and the satisfaction of a navigation receiver reporting strong locks on every satellite in view during a quiet noon. The sun is more dangerous than we once thought, because we are closer to its workings and more dependent on things that notice those workings. It is more knowable than we dared hope, because two bright machines are dipping their hands into the stream and telling us how it flows. The tale returns, as always, to light. A photon that left the photosphere 8 minutes ago touches the back of a hand. A particle in the wind that left 3 days ago rattles a magnetometer. A CME that left yesterday tugs on a grid. A bright loop that formed this afternoon is recorded by a camera behind a titanium mask. Parker registers the jostle in the wind. Solar Orbiter records the loop that started it. The Earth hums a little louder for a few hours, glows at its crowns, and then settles. Instruments file their reports. Engineers read them. Forecasts are updated. Somewhere a child sees the sky move and learns a new word. Somewhere else, a team rehearses a blackout drill. Somewhere in between, someone lies under a dark window, hearing this story, feeling how knowledge takes the sharpest edges off danger and turns a loud star into something we can live beside with both caution and awe. Parker has been edging closer, loop by careful loop. On the 24th of December 2024, it swept through perihelion, only about 6.16 million kilometers from the Sun, closer than any spacecraft has ever dared, while briefly becoming the fastest human-made object, skimming space at roughly 692,000 kilometers per hour. From that vantage, instruments tasted the magnetic breath at its source and began stitching together how the corona and the Sun's tangled fields lift and sculpt the solar wind. One surprise was a family of magnetic structures that sweep through the low atmosphere like invisible paddles, whipping portions of the wind to much higher speeds, up to about 500,000 kilometers per hour, beyond what nearby regions manage. Another was a hush where dust should have been, evidence for a dust-free zone, beginning roughly 5.6 million kilometers from the Sun, where radiation bakes and vaporizes tiny grains faster than fresh debris can drift in to replace them. Every close pass turns ideas into measurements and measurements into patterns. Solar Orbiter, taking a wider lane, has been returning portraits that feel intimate at scale. Its first close images revealed thousands of tiny brightenings campfires, sparking all over the low corona. These miniature flares, thought to arise where small magnetic fields reconnect, could be the background crackle that keeps the corona hot. From about 77 million kilometers, the spacecraft captured the sharpest views yet of feathery loops and bright footpoints, and, as it roams, it samples the particles along its path. The combination pictures tied to particles help sort the many flavors of space weather into causes rather than just effects. Then comes the part that catches the ear. Space is quiet for us because sound needs air or something like it to travel, and the expanses between worlds are too thin for pressure waves to cross. Yet the Sun is forever launching waves into its plasma, ripples in density, ripples in electric and magnetic fields, and spacecraft can measure those ripples. convert the measured frequencies and amplitudes into what they would sound like if an atmosphere were present, and the star acquires a voice. At Earth's distance, that voice becomes a broad, soothing buzz with a faint electrical grain, something like a power station heard from across a valley. The scale of the power behind it, though, is anything but gentle. The fusion engine runs at about 3.85 times 1026 watts, roughly 1,000,000 times humanity's annual production every second. If air filled the path all the way to Earth, the volume of the sun's composite hum would hover near 110 decibels here, loud enough for a rock arena, relentless enough to deafen a species that evolved under it. Closer in, reconstructions climb beyond what any air could carry. Near the surface, estimates push toward 270 decibels. Decibels are logarithmic, so 10 points higher means 10 times the intensity. Earth's atmosphere caps out near 190 decibels. The sun's voice would vault that cap by orders of magnitude, far into territory where the idea of sound stops behaving like sound at all. Volume isn't the useful thing to listen for anyway. Patterns are. As an imaginary ship drifted sunward through a make-believe medium, the background buzz would start to unfurl into textures. The first clear layer would be the solar wind itself, a rough, gusting tone, rising and falling in ribbons. The wind carries charged particles outward from the sun in all directions, but the way it accelerates remains odd. Observers in the mid-20th century noticed a mismatch. Particles moving around within the corona seemed to have average speeds on the order of 145 meters per second, while particles outside the corona were already racing at about 618 meters per second. Subsonic, turning into supersonic, just beyond the visible limb. Something in the transition region and low corona is giving the wind a push, and not a gentle one. The agent is still debated, but it smells of magnetism. Waves carried along field lines that dump their energy into particles at just the right heights, or tiny reconnection events that fling material outward in countless small spurts. The corona's temperature offers another clue and another riddle. Right above a surface glowing near 5,500 degrees Celsius, the gas leaps to 1,000,000 or 2,000,000 degrees within a short climb. Heat usually flows from hot to cold, yet here the air above is the hotter bath, and the surface below the cooler basin. Waves launched from lower layers and dissipated aloft may be keeping the bath hot. Ubiquitous microflares may be topping it up. Neither story on its own has closed the case. The sun can be generous and stubborn in the same breath. Some boundaries should be audible in principle. One of them is the Alfvén surface, where the solar wind's outward speed first outpaces the inward propagation speed of certain magnetic disturbances. Cross it, and the wind is no longer tethered. It carries the field outward like a flag streaming behind a runner. In the imagination with air, the crossing adds a tremor to the sound, a thin, high shimmer overlaying the rumble, the signature of waves in a plasma beginning to outrun some of the messages that would otherwise run back down the rope to the surface. Past that threshold, finer notes enter. Measurements turned to audio reveal Langmuir waves, the quick oscillations of electrons on plasma's tight springs. They tend to appear in the strong beams of particles that fly outward along funnels rooted in the network between granules. Think of the surface pattern as tiles of rising light with darker seams. Along the seams, magnetic field lines gather like threads. Where threads open, plasma streams. Where streams run, electrons quiver and sing in tones that climb and fall. The sound is kettle-like in character, whistly, insistent, laid over the wind's low growl. Waves in a plasma don't all travel at the same speed. Faster components run ahead, slower ones lag. Their interference makes dispersive patterns that sound like flocks of small chirps when rendered into audio. The effect is akin to rain on a sheet of tin. Individual taps at first, then a texture when the taps multiply, then a kind of sleep-making steadiness when the textures overlap. What begins as a messy spectrum resolves into bands you can anticipate. In that anticipation is a kind of understanding. Another family of tones carries a name borrowed from radio lore: Whistler mode waves. On Earth, lightning strokes set the magnetosphere ringing with brief, downward sliding whistles that receivers can pick up far from the storm. The sun is writ larger. The same class of waves, measured near the star and converted for human hearing, becomes a welter of rising and falling wails, as if thousands of distant cracks have overlapped into a single restless chorus. A magnetosphere, alive with continuous small reconnection, or with a constant flux of fast particles, would sound like that. The sun's magnetic environment appears to be perpetually busy, not quiet and punctuated. Magnetic reconnection is the dry phrase for this drama. The corona is threaded with field lines rooted in a surface that never stops shifting. As convection drags footpoints around, lines braid and shear. When oppositely directed fields are pressed together, they can rearrange topology break and rejoin in new partners, releasing stored magnetic energy in a breath. Large reconnection episodes make the classic looping flares in big, active regions. Much smaller ones, scaled down to what some call nanoflares, may be happening everywhere, all the time. Each is a tiny catapult. Fields snap into shorter, less stressed configurations and fling nearby plasma outward, or heat it abruptly to multi-million degree temperatures. Solar Orbiter's campfires and Parker's in situ detections of sudden magnetic flips, switchbacks, fit as pieces of that story. If nanoflares are as common as the rough audio suggests, their collective heat could keep the bath hot and help accelerate the wind without any single blast having to do the whole job. All of this, wind tones, kettle hiss, chirps, whistlers, the imagined roar up close, returns to the quiet insistence of instruments doing simple things well. Parker samples particles and fields where they are being made and pushed. Solar Orbiter shows where the loops rise and where small brightenings spark. Together they turn mystery into balance sheet. How much energy must be supplied in the low corona to maintain a 1,000,000 degree temperature? How waves and reconnection together could pay that bill? How much momentum must be passed to the wind to raise it from subsonic in the base to supersonic beyond the Alfvén's surface, which features correlate best with fast streams that arrive at Earth days later? The ear, borrowed through conversion from instruments, helps catch patterns the eye alone might miss. The imagination can keep traveling inward to where the volume estimates become absurd, but the useful act is gentler. Picture the low corona, busy with countless small switches, the field snapping in bright pinpricks that Solar Orbiter nicknames campfires. Picture Parker threading channels where the magnetic field suddenly reverses sign and then flips back again, like a ribbon flicked by a hand. Tie those facts to the reconstructed sounds, a low hum that never stops, overlaid by fine hissing and chirping, streaked with 1,000 brief slides. That is what a star gives off when it works for a living. A few numbers settle the mind after the pictures and the listening. The close pass to 6.16 million kilometers tells us that shields and guidance can hold under an onslaught of heat that would roast most materials. The peak speed, near 692,000 kilometers per hour, tells us the orbit design is paying off in daring and data. The measured speed-ups in pockets of the wind magnetic sweeps, adding up to roughly 500,000 kilometers per hour, tell us that the acceleration is not a single smooth push, but a quilt of kicks. The dust-free zone near 5.6 million kilometers hints at how harsh the near-Sun environment is for small solids. Campfires at 77 million kilometers tell us that the corona's heat may be granular in origin, not just global. Each fact is a step on stairs we can climb more safely next cycle than this one. There's a human scale tucked into the engineering too. An 11-centimeter slab of carbon composite with a sun-white face, living in light bright enough to cook a pizza in seconds, keeping the rest of the spacecraft in a pocket of shade. A nest of titanium foils punctured with tiny windows so telescopes can glance out without cooking their own lenses. Autonomy routines that watch the sun's position with paranoia and nudge the whole craft to keep the shield aligned, even when no one on Earth can speak to it for days. Software that decides what to save at full resolution and what to compress or throw away, then holds its memory like a trust until a link home opens. These are tender, practical answers to an old curiosity. How close can we get without being burned? And what will we learn if we do? The lessons loop back to everyday life in indirect but tangible ways. Better models of the wind sources mean better forecasts of when fast streams will rattle Earth's magnetic field. Better understanding of how and where CMEs form and accelerate means more accurate arrival times and hazard levels. More precise maps of the Alfvén surface and of open field lines mean clearer routes for particles that can affect satellites and astronauts. Even the esoterica of dust near the sun matters to the instruments that must look through that dust and to the comets that mine it on their long arcs. Parker's prime timeline was set for about 7 years, and it is nearing that mark. But there is grace left in the flight plan and resilience in the hardware. Each pass offers a new geometry, a new set of alignments with other spacecraft, a new part of the cycle's mood. Solar Orbiter will keep circling with its cameras and particle counters, building a film rather than a snapshot. Between them, the sun turns from a single, bright question into a chorus of answers that keep changing and yet hold tune. Listening becomes a way to think. A clock in another room can be understood by its tick. How often? How steady? When it stutters. The sun's tick is not a single click, but a texture. A humming meter laced with hisses and whistles. The texture deepens when our proxies, the instruments that hear without ears, hand back what they felt. Somewhere in that texture is the explanation for a wind that shouldn't be so fast and a crown that shouldn't be so hot. Somewhere, too, is the long comfort that a dangerous star can be known well enough to live beside. The next time the night is quiet, picture that low electrical buzz under the world, steady as tide. The mysteries remain, the answers are arriving, and the song of the sun, translated into air and patience, is turning into understanding. You're right to imagine that if a small, heat-shielded craft can graze the sun's atmosphere, then surely a sturdier container could carry our worst leftovers there as well. The wish is understandable. Plastics that outlive generations, landfills that seep and sprawl, chemical and biological hazards that demand meticulous care, and nuclear byproducts that stay potent for spans measured on the scale of civilizations. These are heavy thoughts to carry to bed. A star feels like a final answer. Load the trouble into a capsule, light the engines, and let the sun take it. Simple in a picture, complicated in the universe we actually inhabit. The complication begins with a sideways truth. Earth is not sitting beneath the sun like a dartboard under a lamp. It is running laps at about 30 kilometers per second. That sideways speed, balanced against gravity's pull, is exactly what makes an orbit. If you go straight up from Earth and keep that sideways speed, you don't fall toward the sun, you join Earth in circling it. If you want to fall inward, you must erase the sideways component. In space, there is no brake pedal. You brake by burning fuel in the opposite direction of your motion, until your inherited 30 kilometers per second is gone and gravity has you by both shoulders. The numbers that sound modest on paper become waterfalls when you try to climb them with fuel. Leaving Earth's gravity well demands about 11.2 kilometers per second of speed just to reach escape velocity. Rockets earn that with stages upon stages of propellant. Then comes the heliocentric problem. Canceling 30 kilometers per second. The closer you are to the sun, the faster the orbit. So the deeper you dive, the bigger the bill. Mercury, tightly bound, whips around at 48 kilometers per second. Pluto, far and loose, drifts at to 4.7 kilometers per second. It is often cheaper in propellant to go the wrong way. First out toward the suburbs of the solar system, slow there where motion is gentle, and fall in on a long arc, than to fight toward the center from the start. Elegant orbital mechanics, punishing logistics. A rocket's life is ruled by a simple, stubborn fact, often called the rocket equation. To change speed, you throw mass out the back. The more speed change you need, the more propellant you must start with. Carrying more propellant makes the rocket heavier, which means you need even more propellant to push the propellant. It's an exponential spiral. The Saturn V history's moon chariot burned on the order of 2 million liters of propellants, just to toss a few tens of tons onto a path that grazed 11.2 kilometers per second, retiring 30 kilometers per second in heliocentric flight, with a heavy, armored canister of waste. That's orders of magnitude beyond what our launchers can lift in one gulp. You could try to stage it, launch the waste container, launch tanker flights to meet it, refuel in Earth orbit, spiral out, then burn hard retrograde. Each extra step adds cost, complexity, and failure modes. Space treats hubris like a physics problem. There is a gentler technique than raw thrust. Gravity assists let you steal a little energy from a planet's motion, or pay a little back, depending on how you thread the encounter. We often brag about the speeding kind, the slingshots that sent the Voyagers outward, but you can reverse the trick. Approach a planet from behind in its orbit, dip low, exit behind it, and you leave a sliver of your heliocentric energy behind. Repeat many times, patiently, and you can unwind your sideways velocity without hauling impossible tanks of propellant. The price is time and precision. Bepi Colombo, on its careful way to Mercury, will have used 9 assists by the time it settles into orbit. A disposal mission needs similar clockwork, a string of planetary flybys, each with narrow windows, each demanding burns and guidance, each with risks. When the payload is science instruments, we accept the dance. When the payload is concentrated hazard, every step asks an ethical question. Is the next link worth the added chance of failure? Launch 2 is never ordinary. Even the most reliable families of rockets have failure rates that are small but real. We accept that for telescopes, weatherbirds, communications, satellites, probes, a launch mishap in those cases is lost money and knowledge, sometimes debris, sometimes cleanup. If the cargo is high-level nuclear waste, biohazards, or toxic industrial concentrates, A failure close to home is an avoidable catastrophe. You can layer containment upon containment. You cannot make the risk zero. And even after a clean liftoff, years of operations stretch ahead: valves, sensors, orientations, thermal cycles, micrometeoroids, the long list of small things that can become big things in unforgiving environments. The more links in the chain, the more places for the chain to part. Cost is not the villain, it is the mirror. Every budget line for "throw it at the sun" would come from somewhere else. Advanced recycling and redesign that makes fewer poisons in the first place. Vitrification and deep geologic repositories that seal what must be sealed behind many passive barriers. Reactor designs that can transmute long-lived waste into shorter-lived products while making power, cleanup and monitoring for the communities who live with the legacy of our industrial century. Space can, in some cases, reduce risk here on Earth. It should not become an excuse to export responsibility. A different version of the urge, if not in, then out, sounds better and is, in narrow terms, easier. To leave the sun altogether from Earth's orbit, the needed heliocentric speed is about 42.1 kilometers per second. You already ride along at 30 kilometers per second with Earth, so the extra is 12.1 kilometers per second in the forward direction, apart from the climb out of Earth's gravity well. Clever mission designers can stack maneuvers to exploit the O-berth effect, burning at deep perihelion, where your engine's work buys more change per kilogram of propellant because your kinetic energy is already high. But getting to that deep perihelion with a hazardous load means skimming much closer to the sun than any waste container could tolerate, then lighting engines exactly when heat and radiation are most intense. The math is satisfying. The practical steps are unkind. Even if you solved those and flung a capsule outward at escape speed, you would still ask whether it is right to make a problem vanish into interstellar space rather than reduce it at the source. The useful end to the thought experiment is not defeat, it is orientation. The sun is not a furnace waiting for our mess. It is a nearby star circled by a small world that must learn to live within its own cycles. The orbital arithmetic that thwarts our easy plan is the same grammar that lets Parker dive safely, that lets Solar Orbiter linger at the right distances, that lets forecasters warn a grid before a storm brushes our field. It's the same grammar that steers satellites we depend on and keeps navigators honest. Knowing it gives you a quiet confidence about what can be done and what shouldn't be tried. Closer to home, there are choices that work with time rather than against it. Multi-barrier storage that relies on geology as well as engineering. Materials that can be recovered rather than buried. Manufacturing that avoids forever chemicals. Power systems that don't produce long-lived legacy hazards as a routine output. None of that is as cinematic as a rocket arcing toward the Sunday. All of it is kinder to real air, real water, and real people. The thought of the sun as a solution does one more small, surprising kindness. It returns us to the scale of gratitude. We began, many pages ago, with the journey of a photon. We followed it backward through our eye and the air and the vacuum to a core where collisions both improbable and inevitable knitted hydrogen into helium and paid for a universe of mornings. We listened to the stars' translated voice and learned to hear patterns in what first sounded like a single, endless buzz. We watched storms ripple through a magnetosphere and touch wires and screens. We flew, in imagination, beside a carbon shield and a titanium quilt, and learned that proximity is paid for in precision. We weighed the fantasy of using a star to erase our least graceful products and found that the math and the ethics both urged us back toward the ground, where responsibility lives. Hold that responsibility lightly as you think about dawn. The photons that will sketch color on your wall tomorrow have been on the road for a very long time. They were born as gamma rays in a core that has never seen dark. They knocked around inside a furnace for hundreds of thousands of years. They traded energy and direction until at last they could walk straight through a thin surface and fly the 8 minutes between worlds. They will touch a leaf and be turned to sugar. They will warm a hand. They will glance off ice and teach an instrument what kind of clouds are present. They will scatter blue into a sky and pink into a low bank of clouds. They will set a small scene in a kitchen and disappear. None of those destinations is a waste bin. All of them are uses. That is the mood to bring to the ordinary problem of trash. Not exile, but design. Not erasure, but change. The sun will keep its rhythms while we learn ours. Its magnetic breath will swell and soften. Its crown will flicker with campfires too small to see without building the right eyes. Its wind will speed and slow along channels we are only now naming. Parker will edge in again and taste the switchbacks. Solar Orbiter will catch more of the tiny brightenings and watch them scale upward in storms. Forecasts will get a shade earlier and a shade more accurate. Power operators will treat a predicted gust in the solar wind like a mariner treats a weather front expected, respected, navigated. Somewhere, Aurora will creep down into a city that doesn't often see it and paint quiet faces green. When the mind wants a closing instruction, give it something soft. A good ending is only a pause in a longer attention. If this wandering through a dangerous, generous star helped you find calm, helped you match a big universe to a quiet room, a gentle tap on like and subscribe keeps this little harbor easy to reach again, and sometimes helps another traveler find it. Then let the night finish its work. The hill where we started is still there. The sun is still turning fuel into morning. And in a world that thinks well about what it makes, and what it keeps, and what it chooses not to make at all, the next sunrise will feel not just beautiful, but earned. Let the hill grow quiet again. The star keeps working. Fuel turns to light. Light drifts to air, and air softens into color. We trace that path tonight back through the photosphere's grain, the million-degree crown, the restless wind, all the way to a core where pressure weaves hydrogen into morning. We listened for its hidden music, heard storms that can trouble wires and paint the poles, and watched two small messengers, one tasting the wind, one watching the flames teach us how a dangerous neighbor can be known. We even carried a harder question to the edge and set it down. A star is not a furnace for our forgetting. Wisdom is nearer, use less, design better, care longer. Hold the whole shape lightly now. A living sun with a steady beat, a patient earth turning beneath it, and you, somewhere in between, breathing in the calm that understanding brings. Nothing more is needed. The next dawn is already being made. If your thoughts keep moving, let them move with the slow tide of light, crossing space 8 quiet minutes, then a window, then a room. When sleep comes, follow it. The story doesn't end. It simply goes on without you for a while, carrying you forward toward morning.